Good afternoon. I welcome on the behalf of HRD Cell to all of you on the second day of 1 week faculty development program on electric vehicle powertrain simulation using MATLAB and real-time simulator. Today we have Dr. Naveen Yela from IIT BHU. The topic of his talk is reduced device count, medium voltage, high power factor correction converter for future transportation. Before inviting him, let me introduce to Mr. to Dr. Naveen. Just give me a second. Dr. Naveen, of course, he is one of my very good friend, but let me introduce him officially. Dr. Naveen Yella received his BE degree in Electrical and Electronics Engineering from Andhra University, Visakhapatnam, India in 2009. He has completed his MTech degree in Power Electronics and Drive from National Institute of Technology, Kurukshetra in 2011 with gold medal. After that, he did his PhD degree in electrical engineering from Indian Institute of Technology, Roorkee in 2019. He worked as assistant professor with Pandit Deen Dayal Petroleum University, Gandhinagar, India till 2020 and National Institute of Technology, Tiruchirappalli till February 2022. He is currently working as assistant professor with the Electrical Engineering Department in Indian Institute of Technology, BHU, Banaras Hindu University, Varanasi. His research interests include power converter, multi-level inverter, EV charger, and renewable energy sources. He published several papers in a good journal of repute. So I welcome to Dr. Naveen to deliver his talk. Over to you, Dr. Naveen.
Sir, good afternoon. Thank you for
Very
this
good.
opportunity.
Very good
And
afternoon, Naveen Saab.
अरे सर सर ये तो इट्स अच्छा नहीं लग रहा है. So by the way, nice opportunity for me, sir. Sir is my mentor, what not. So he's my senior under the same professor. So it's like good time with you, sir, at IT Roorkee.
Yes, yes.
Sir, okay, that's once again thank you for this opportunity. So I'll start, sir. Yeah, so good afternoon, all participants. And I think is very, today I would like to share my experience or otherwise my understanding about these configurations and the scope of these configurations in future or upcoming any application. Specifically, like we are trying to target on transportation. Uh, uh, so in this context, so as you know that. There are international platforms or forums, or they are having their own set standards to meet the carbon emission net zero and all. Right. The one of the sector is like transportation. It's like major contribute one of the major contributor for green GHS greenhouse gases. So here, like, how can we as a power electronic engineers can contribute to make clean transportation? As you know that there are based on the loads, right? These are configured, the light load and medium load, right? And upcoming, the heavy load, for example, mining industry or agricultural industry, if you see. Those machinery, what we are using in those sectors, definitely with supposed to be have high capacity. So in this context, what changes are what already advanced countries are adopting? Do we need to do that or otherwise else anything? So this is what actually I would like to share with you guys. Come with the conventional at present charging infra. If you see, so there is a AC, and then AC to there is a two stage conversion. The first stage like power factor correction stage, and the second one is like DC to DC to match with the required voltage of battery, right? So if you see at this front end level, what are the basic requirements? The requirements of the front end converter is such a way that needs to regulate this voltage and also tries to maintain the input current nearly unity power factor. So because there is a grid code, even some standards put that limitation. Not only overall THD, specifically if you say IEEE 519 2024, also as mentioned, not only overall THD, they are also mentioned with the specific harmonic amplitude. So, for example, the dominant harmonic is fifth harmonic. That also has mentioned that that dominant harmonic amplitude must be less than some specific value if it is the rated current or the current which is drawn by the load is beyond or met with some level, like for example, more than 20 amperes, so on, so on. So, in this context, this plays a absolutely very important role. Next is second stage will we are using to match the voltage profile of battery as well as the galvanizing isolation, and these are the important thing. Now, however, if you see at present, right, there are three issues in fact. The issue number one is if you talk about power electronic converter or power converter unit, so one is efficiency, is most important performance parameter. Second is power density. Power density is not always true for the all applications. Rather, it all depends on your area or where we are really talking about. For example, marine applications, space applications. There, the space is most important. Most important constraint. That instant, the power density will play very key role. It will be a one of the most important parameter. And the third is the reliable. The system should be more reliable. So these are the three important performance parameters every power electronic engineer usually think about or thought about. However, definitely it should be effective. All XYZ will be definitely be there. However, if you see this efficiency wise in the literature also, the research is almost met with 98 percentage. In fact, some configuration more than 99, more than not around the 99. It's good. The number also very decent. Further, who wants 100 out of 100? Even if someone gives what matters. So I'm not sure exactly in which application we need 100 out of 100. In fact, it is not practically also not possible. So 99 is a good number. So the second one is the power density. So how can we increase the power density? I mentioned it, for example, even a simple example, classical example, if you see onboard charger, their entire charger, battery, all the stuff sitting in your vehicle only. So the more space it is occupying, it obviously there is already there is a constraint to travel more distances, and itself is a like bulky heavy, more less power dense, then again one more additional disadvantage. So which elements are really occupying this more space or otherwise decreasing the power density? So there are two important passive elements where we are using. We in fact we cannot escape those. One is inductor, magnetics, and another one is statistics, static field. That is what capacitor and inductor, right? So if you see this AC to DC power conversion, what we are using, the capacitor we are using to establish DC link, a stiff, a regulated voltage. So obviously, the more voltage you, the stiff voltage you require, the large capacitance you need to, number one. And another one is like inductor. So this is where we are using to shape the current, right? To meet your power quality. So here, how can uses this size, right? So one way inductance and 5 by I as the basic definition of inductance. So number of turns I per unit. If you see the flux is equals V to area. You know, even with area product. Usually, if you design any inductor, what we have to take the area product is general method. Everyone usually we are following, right? There we have to choose a magnetic material to meet your requirement, like flux density itna hona chahiye, so on. Some there is a very systematic step by step procedure if you want to make high frequency transformer or inductor. So in this one, uh, for example, if you design a core, hybridize a core material ke saath, if it offers like high saturated level and high flux density, that is very good. But we are electrical engineering engineers, we are not much command on the material science regard. So therefore, another parameter where we can control, or we can we can reduce the size of any magnet is the frequency, right? So frequency into area equals to constant. If you increases the frequency, operating frequency of that inductor transformer, if you increase, the net area will be decreased, the remaining will be constant. So this is one of the very well-known relation. So in this context, if you increases the switching frequency, it's absolutely, this is the one of the possible option. But like increasing for what? At what level we can increase is the question mark. Who will decide? Definitely your switching devices will define how much switching frequency we have to choose. And then that again based on the availability, right? So usually these are the silicon devices and WBG devices, very popular right now. The silicon, again, silicon based MOSFET and IGBT. So IGBT is there, then FET is there, and these are also FETs, silicon carbide FET and gallium nitride wala. These are all FETs. So as you know that around 20 kilohertz you can go with. Here it is 100 kilohertz. It is around more than 300 to 500, 300 to 500 we can, and more, nearly 1 mega. They're promising. In fact, the devices are promising no more than that, but it is like tested conditions, I can say. It even in fact like in my lab itself, we tested this both these devices with driver circuits. It is working. We went more than 800 kilohertz only, not 1 mega. But tested at like 300 volt, 10 amperes. It's running nice, but there are other issues. We will see. So the silicon devices are this, but rating wise is very good. In the market maturity level, if you see this, okay, 100 amperes is at least 3.3 kV, and this is more or less also the same stuff, less power rating than the IGBT. But this is like 1200 volt, nearly 60 amperes is its mostly available device. But this is 650 volt and 40 amperes is the mostly available device. So in this context, now come back. So if you can operate with higher switching frequency, it's not only sufficient parameter, and what power rating or voltage you are testing is another important parameter while choosing this device. So increasing the power density to operate higher switching frequency, these are the best choice. But availability के साथ if you see this is 650 volt 40 R, ठीक है. Special device, if you put some more money, you may get that 60 amperes also, gallium nitride. But most available devices are this, right? More or less, these are again SMD. It's not like through whole. Well, we have not. And now today the devices are coming with the even SiC, silicon, four terminal devices also come. Anyway, this is not exactly relevant for us. The concept is this: For my, here we have to discuss about the future transportation. Even onboard charger, if you see, 72, 48, 380. Now people are talking about here Indian context. It is 800 volt. Europe already shifted it. So here the question mark. If further, if you want to go, that much of high voltage will sit in your vehicle. If you want to charge that battery, right? So the power converter supposed to handle with this voltage rating. So conventional in this context, if you see, I'm going. If you see the PFC, the totem pole is very popular. If you see this, so what is the this is the PFC stage, right? And the later on DC also. Now, if you see this story, if you see, what will happen, what is the minimum device rating, the device rating supposed to be a total DC link voltage. It is like a 300 to 400 volt. Like if you in the resonant LLC people are using very popularly, so for 300 to 420 you take it, so let it 400 volts. If it is 400 volt, the switch is supposed to block at 400 volt standing voltage. If you take this, operating safety 1.5 times, then if it is the case, if it is around 600 volt. Minimum 600 volt device is needed if you want to operate at 400. So this is the point. The futuristic, even if four-wheeler, they are expecting to operate at 800 volt, because like there are two advantages. The V, if you increases VIT is like story energy, so battery ka story. So if it is this is increases, keep I is constant, T can be reduced so that you can make it battery charge very fast. Or otherwise the infra is VIT. If you fix the T is constant, there is another relation you can derive, I can be minimized. So I can, the moment I is decreased, it's not the simple charger. This is the case. It's not such a simple line it is. If you see charger is charger, there is a big cable will draw, right? While charging. So this is also like really consuming, sufficient significant value. So how can we minimize this? The bit increases the voltage so that current can be minimized or reduced, so that corresponding losses you can also minimize. This is the another advantage we go with the bit high voltage. And second is like I mentioned, like specifically mining. There are dumpers. Sorry, there are dumpers, big heavy trucks, and conveyor belts are there. All are heavy machinery. The machine like motor rating, if you see even some specific cases heavy load, 11 kV machines are using. How can you control? So drive only at the end of the day. So if you like now, even recently Reliance wants to move towards the battery powered these vehicles instead of the diesel based. How they want to do? They want to establish the DC rail like a traction rail. So want to establish a DC rail 1.1 kV, so DC, and then they want to extract like a pantograph story only. There are different challenges. That is a DC. There are challenges are there, but they are working on it. So means what? India also industries are looking wherever it is possible. They want to use this battery powered. I don't know really how much reliable and what scope it is having. There are other studies supposed to definitely taken care. But at this level, people are like willing, wanted to shift. So there is an opportunity for us. That is the point. So the 800 volt, if you want to talk about, is it possible to use this totem pole to meet the 800? Obviously, if there are yes and no cases. If yes, with the IGBT and MOSFET and silicon carbide, no, absolutely with the gallium nitride. Why should I go with the gallium nitride? I just mentioned it. Our aim is supposed to be like to meet high power density. So in this context, what will be power density if you want to meet and also go with the bit like 400 to 800 or above. So how can we like use the WBZ devices is the interesting point where we a bit want to focus. And then these are the the statements everybody know. So here the come to the next one is like V2X. So there are classical old stories. This is the V2X people are talking about. So as you know, many of them are must aware about this V2X story. It's more or less it's a storage device. So battery energy storage, so it can be used for wherever you want. Then who will really who will decide when to use? Can we use? Definitely economics will take it. Will drive this. So for example, charging you are spending more, and discharging there is no worth to it. Then what is the logic? So I am spending some money to charge my battery, and like with free of cost I'm using logic in here. So this is the where the question, Indian context, the dynamic pricing, few metro cities to charge these batteries are already introduced up to my knowledge, but I'm not exactly sure about it. But in the original overall, the dynamic pricing not yet done. If it is so, then it may play very key role. Number two, this one, which one? Solar, PV based, photovoltaic based charging infra. Because God gifted, we are a tropical country, we are having good enough insulation, solar energy. So we can also use and to store this during office hours. So this is, though it is a very classic point, but as of now we have not implemented at many places. So there are other bottlenecks. There the researchers are like policy makers supposed to take care. We will see all the stuff. Uh, okay, so this is V2X story, and then now we come to point this. You see this now. There are two cases I have mentioned that if you want to meet, okay, I forgot to discuss about this. So there is a inductor minimization. You go with like higher switching frequency. That is good. What about capacitor? The electrolytic capacitor ka kya story? So there is a, see why we are using this. So there is a good use of it. This is let it AC to DC, I did it, and then DC to DC. What will happen? Any load change, it's not directly reflect on source. Rather, it's like a decoupler. It can handle a small fluctuations due to the load, right? If it is not the case, it has to like all the fluctuations are demand supposed to meet by your source itself. So, but it is really bulky. If you see any inverter, frankly speaking, it's not about not the devices where it is occupying space. Frankly speaking, the electrolytic capacitor, if you see that it itself is a bulky, and otherwise, like and life of this inverter also will be decided by this these capacitors on passive elements. Switch is what? Switch is very less. Itna, I think. If you see this, this is what actually I want to show with you. This is a driver with which can handle, that is what 800 volt I mentioned. Sorry, 800 kilohertz I have mentioned it. So what I want to tell you, see, the Texas is like, it's out of our imagination, frankly speaking. You see this. So that elements are very thin in size. Ajkal, like, fully controlled, auto-controlled devices also coming. So don't expect like these are occupying more space. No, not at all. The inverter are futuristic, any power electronic converter, mostly the space occupied by those passive elements. So how can we, now these are the, what they are doing, this one uh, people are working on it, like though it is classical story, but like they where we want to use, how can we use the really question on it. So what they are doing, it is AC to DC. Instead of AC to DC, you remove it, and simple pulsating, you please bring it to this side. This is what for we are using. If it is single phase, like 2 omega component and higher frequency component needs to be taken care, and then remaining it will send it. So if it is not the case, it will be like this only. No problem, send it this way. So it is in high frequency, it is AC only. So high frequency and send it to this side. And actually, this is one way. Another way also this way. If you develop, do this story and transfer it and rectify it and then filter it. rectify it and filter it, then what will happen? This will be, so this will be happen, and then filter it, and then later on you will get the around DC. So this way they are removing this bulky electrolytic capacitor. However, but I mentioned it. See, there are other topologies. There are other charging infra also. Someone is saying that some portion of 2 omega sending to the battery also not much, really not much serious factor. However, it is a fact. It is really deteriorates the performance. But like there is good literature on this. So people are working on, like, if you send the 2 omega component to the battery, what will happen? That is also people are working on it, right? If you don't want to send it, then what is the procedure? What we have to do it? So one way we have to do a buffer. What the buffer? Only the only filter element के लिए I want to suppress the filter. So I think there is a one more element called APM, auxiliary power module. What it is? It is more or less one more DC to the low voltage battery to meet your auxiliaries, like glass, mirror, and no glass के लिए, and what wiper, all the stuff के लिए. So for that, like, now people are talking about 12 volt. No, now they also wanted to move to 48 volt APMs. APM is like, it's a DC buck boost only, bidirectional. There are other configurations also. What they're doing, the filter of this APM, they want to use to suppress this 2 omega, because when the 2 omega will come while it is charging, this is not the story. While it is charging, if you want to charge, what will happen? The charging only, 2 omega story will come. If it is single phase story, because I'm talking about, okay, there are different aspects. One is like low power at like household, or otherwise heavy vehicle. Well, three phase, there is no 2 omega story. Only ripple is there, switching ripple, that you can suppress with this filter. So this is one of the approach to minimize the size of the electrolytic capacitor. Or otherwise, matrix converter is very good example to avoid this. AC to directly high frequency AC and transfer it and rectify it and convert it. That is also one of the approach. There are different approaches. So these ways we somehow we can address the size of these two passive elements. Now, okay, so here I would like to like focus at the front end. Based on the availability time, we will see. So AC to DC, what it has to take care, it's supposed to provide a stiff DC voltage here, and then needs to take care about the source current also. So there are different applications where we are using today, present day this AC to DC power conversion, railway traction, and then this is marine, and this winds of course too, and then integration of this also. So these are old classification. I have not changed actually. Somehow a few of them may not, maybe more knowledgeable than me regarding the statistics. This is like ultra, super ultra. There are classifications are there, but still, if you discuss or continue with the fine point, where can we use the WBZ devices? If you want, where we have to use, at what power level, so restrict for some time. If you restrict our discussion for like OBC chargers, then yes, there is a scope we can use these WBZ devices, right, to this. So thanks to the Texas Instruments application note. See, these guys, I told you, they're always like ahead with us. So you see this, what they did it. Okay, if it is these devices are available in the market, and really how they matters. Now you see this is a totem pole. The totem pole has one more inherent constraint. The zero cross has some issue that has to taken care by your controller. That is the one of the important point we need to. However, you see this one. Now here is the totem pole is not new to many of them. Here the interesting thing is what they did it. You see this, they changed one leg with the high frequency, specifically gallium nitride, because 400 volt DC link they are talking about. So 650 volt you require. 600 is minimum it require. So there 600 volt is available. As you go with this, and these are again, you see, these are silicon FETs only. So silicon FET, why do we require, like silicon is sufficient? The point is very simple. These two devices will operate with higher switching frequency, and these two devices will operate at a line frequency. That is 50 hertz story. Because sufficient to get the same performance. So as you know, these are the way they are controlling. Number one, actually, I think you know that uh, this is AC, and this is the AB. Let it. This is VAB. This is VAB. This is VAB and V input, V source. This is LS, where this is the current I supposed to control in such a way that it should track my input voltage. So in this context, what they are doing, that control, current control. See, if you choose a higher switching frequency, let it like this is a constant only. For high frequency, lower time, consider the inductor current is, though it is a sine wave, it is very very small instant. If I'm talking about this is switching, so how can I control this current through the inductor? Slope. You control the slope of the inductor current so that it should track this. So increasing and decreasing. Increasing definitely by what? Increasing is Li is equals to Vs by VAB, LdI by dt, where dt di is equals to this one and this. So that this will be positive when and only when this is the case. If this is a negative, there are like if it is the case, what will happen? Positive. It should be a positive. The result will be positive. So when and only when VAB is equals to 0, where VAB is equals to negative voltage. So if it is VAB is equals to positive, positive VDC, this is a VDC you call it as. What will happen? The current is a decreasing slope. Here it is increasing slope. This is a decreasing slope. So this is the way you can control the current through the primary or source inductance. That is well known fact. Okay, so but instead of deriving the plus VDC to minus VDC, the plus VDC to minus VDC is a ripple is like double. So two times like 800 volt. The more switching it is, once it crosses 150 kilohertz, you need to take care about one more parameter called EMI and EMC. This is most another important and most dangerous thing. So therefore, the more dV by dt, obviously the more headache for us. So the people are using the unipolar rather than this story. However, however, there is one more advantage if you want to integrate directly this structure, split capacitor structures to DC, because the DC to DC, what will happen? The DC to DC high frequency chahiye. High frequency, this is a high frequency AC only, though it is a input DC, then transfer it, then the same will come here and rectify it and filter it so that you will get the DC. So that is the advantage if you use this type of bipolar. There are different approaches, so that is the different discussion. However, what context we are talking about matters a lot. That's it. So PFC, if some cases the dV by dt is very high, so that we don't want to operate plus VDC to minus VDC. But some cases, if you want to integrate the capacitorless, active power decouple, very popular for EV chargers. So there, I don't want to use better you directly generate the square wave, or otherwise this rectangular wave or square wave. So then directly transfer it and do that stuff. It's very good option. And then if you provide a small one more delay here, this delay if you provide, so our advantage is like softer switching can be possible. So these are the few aspects that is different. So therefore the Texas Instruments, what they investigated, one leg they used with high frequency, another leg they used for line frequency, sufficient to control the input current and this. So it is having the two loops, classical approach only, unit template theory only they are using. So this is a DC needs to be controlled. So therefore there is an outer loop and there is an inner loop. So this is the case. There is a PI regulator. Now the question comes: hysteresis you can use directly controller with current controller, or else if you want to use PI, a steady state stability never be zero because it is always having some frequency component, and steady state error for this change, a spike, never be a zero. So advisable if you want to handle with the instantaneous PR is like good option, or else hysteresis directly is a wonderful option. However, you know the limitation of hysteresis controller. Any change in the load directly hit or see, for example, what I mean to say, if this is this one, so the hysteresis band will be like this, right? So if it is load change, this will also change. So therefore, if it changes, the switching frequency may change. The switching frequency is not constant. One of the biggest challenges filter. It's not all the filter variable filter design is not easy at all, right? So how can you choose the filter? Once you fix the operating points accordingly, L value come to the picture. So therefore, hysteresis is there the limitation, but however, for current control is a wonderful. It will really hold the current shape and wants to track the whatever reference you have given. That is the point. Or else the constant DQ, constant values instead of instantaneous values, then PI is absolutely good option and you can go with that. So inner loop will take care about the this one input current, and outer loop will take care about the DC link. Second is like what they have done is interleaved. Still it is, you see, still it is 400 volts. So existing EV charger only, 300, 308 volt, let it be. So for that instant, front end stage like 400 volt, and इसके बाद 400 to 380 and 400 to कुछ भी हो सकता है. We can use one more intermediate stage. Sorry. So if I want to increase this, that's what. If I want to decrease this my time, and if my battery is like good cycle capacity, then how can I increase this the current capacity? But this device is not much matured and not can handle high current rating. That instant it is hardly. So how can you increase the capacity? Paralleling. So this fellow did the paralleling of this control device instead of this. So this way, like the current when, because it is silicon, we have a good current rating. That's the what they want to convey. And then another one is like NPC. So just I mentioned it. Here, if you see, this is AC. If I want to go with the 800 volt, right? So conventional two-level topology can be used with the gallium nitride? No, obviously no, because 800 volt, it needs at least 1.5 times of 800. That is a 1200 volt. So we have exactly 1200 volt for silicon carbide. It is not about the gallium nitride. Number one. So still, so therefore, what you have to do, a WBG, if you want to use, you have to change your configuration. Number one. Number two, okay. If you want to change, you see this. These are the, again, silicon devices only, but these are the WBG. As you know, these devices will offer good characteristics, electrical characteristics, like, the on-state resistance very low, and junction capacitance values, obviously GAN है तो है नहीं, almost negligible है. So these are the few really good advantages they are offering, so that we can operate these devices at higher switching frequency. It's my knowledge, my understanding. If I am wrong, please check it from your end also. This, like, safe operating region, that is most important character while you check your data, any data sheet of a device, that will tell you all the story actually, right? Okay, another thing. Okay, so see what they have done it, like they changed the silicon carbide SiC diodes. Okay, then why we need to do this? So as you know very well that diode loss, conduction losses is more than the control device. Because like constant voltage, knee voltage of this device at least like more than 0.3, right? Give me a second, थोड़ा connection issue चल रहा है.
Sir, it is absolutely fine.
अच्छा सर, मेरे को एक पॉप आ रहा है. अच्छा अच्छा अच्छा, ठीक है, मैं वीडियो का बंद कर दूं. सर, so NPC, yeah, yeah. See, so what I've done is obviously conduction losses of this uncontrolled devices more than the controlled device, because cut-in voltage is like even conventional classical silicon, if you see, 0.7 volt. So it is zero point 0.7 into 100 amperes if you see 700 volt. And then if it is controlled devices, if you see, its saturated voltage is like zero point 0.1 to zero point 0.2. It's absolutely a significant value in respect of loss, specifically conduction losses. And another thing, like, yeah, what about conduction? What about so therefore, if you want to replace with these diodes with the control, it's good option. Or silicon versus the other WBG, some other devices which will offer the low on-state resistance is also one of the good option. But another thing is like this configuration 30 years back, no, Professor Akagi was invented this. And इसमें क्या, this is very clear, and each devices, control devices needs to block off of the DC link voltage. Now, just I mentioned it. If you see this structure, if it three level, if it three level, what voltage you can synthesize at the pole voltage? It is about more or less this one, this one. So if you somehow operate this, there is an opportunity. I can also operate, such a way that this will offer like this. And this is what actually sorry, this is three level: positive VDC by 2, 0, and minus VDC by 2, and this is the case. So if it is the case, just I have mentioned it, if this is what output of your AC to DC at DC level, if I want to integrate this with your LLC, we take a very classical LLC structure. And then what is LLC structure? AC, high frequency, there is a DC, this is the case. This DC2 can establish high frequency, or otherwise directly you can connect a high frequency transformer here and rectify it, AC to DC, and filter it. So this, if I have across here, so great advantage, right? So there is a natural zero voltage is happening. So ZVS is possible, number one. And number two, it is three level structure. So there are three level. So in devices stress also is low, number two. So that way I can, and of course it is, see, it is a doubler also. That is then one of the disadvantage you can claim, or advantage you can claim. It is voltage doubler. The common point is connected with the neutral. So the, if it is 230 volts, peak is like 326 volt. And so therefore, like, doubler will be what, VDC by 2 is equals to peak of your source voltage. So therefore nearly 700 plus volt or 800 volt. So this is one of the great advantage if you use this such a structure at PFC. It will also take care about power quality, and also minimizes the one more bridge here. I think you are trying to, I think you are following what I am trying to convey. Here it is like there is a what I mean to say, DC to AC, no, like bridge is there, no, bridge. So that bridge I avoided, and using this three level to go with higher DC link voltage, and also establishing this and transfer to this, some good advantages are there in addition to the wave shape. That is important thing. And see, context is different. I'm not talking about like power quality alone. We are discussing about like integrating WBG devices with the classical conventional structures. If it is so, what is most available or suitable? That is the question number one. And inherently, these multi-level are offering power wave shaping. That is additional advantage. We have to consider it. Third is, third immediately point will come, like it needs more and more, of course, needs a devices. That is most important clumsy point that we need to address, and they are addressing also. So availability of the devices to meet the high voltage power rating, load power rating matters. This, in this context, we are we are discussing. It is not the classical NPC. NPC, many of them are know that it's not required me to discuss the NPC story here. So again, the two level itself, a three phase, we know that why do we shifted to the three phase, high power handling capacity, इसलिए हम लोग three phase में भी जा सकता है. Yeah, this is Professor Kohler is introduced. Now this is called Vienna. Long back it has introduced. However, See, this is again what they did. The Texas did very nicely. These diodes replaced with silicon carbide based, but these are again silicon only. Why do we like silicon are sufficient? This is a quadrant, four quadrant switch, and this supposed to block the half of the DC link. What is the voltage rating of this device? If you see, if I want to turn on, so this point will come here. So this is already connected here. So this will be, the diodes must be blocked if you have a VDC, and the total VDC needs to be blocked, and these are VDC by 2 only. Sir, am I audible?
Yes, yes, you are very much
Acha, acha,
audible,
acha,
Naveen
acha,
sir.
sir.
Yeah.
Sorry. Then continuously there is interrupting. Okay, VDC by 2, and oh yeah, these are the VDC by 2. But see, obviously, these are the diodes, so therefore it is unidirectional. The V2X story won't work at all. Okay, keep one that point aside. Otherwise, what is the advantage over the NPC? If you see, the devices count are like obviously low here. Number one. However, the voltage stress across these diodes definitely very high than that. So, and most important thing is like these diodes we are using to tap this positive DC rail and negative DC rail. So high voltage. So this is another important point. So this is the biggest constraint here, because highest losses will take care if you will takes place if you operating at unity power factor load. I'll coming slides we will also see that. Before that, you see. So what is an additional advantage here? If you see this four quadrant switch, some in the literature, some of authors claiming that this is a single switch. I don't think so. It is a single switch, because though it is you know channel in the platform may be a common. However, in kind for them control. How can you give a control internally? You can use a not signal, but the driver is like supposed to be no different only. For this switch, driver must be different. For this also driver must. There supposed to be independent individual driver circuits. The moment it is a driver is different, all the story is again same stuff, same it has to be followed. However, the control, yes, internally in the driver itself you can also use the control, not gate complementary, so that you can also give. So there is an advantage. Otherwise, around I don't think so. It is a single switch. It again, I don't know. It's my understanding. This is not exactly single unit. It is two separate entities only. Okay, if it is the another, okay, if it is so, what is an advantage? Something wrong, something happened to this device. This is happened. So how it acts like? It acts like a simple uncontrolled rectifier itself. So though you have a like anyway, these are bulky filters we are using, but at least like for drive application, you don't need too much bother for some duration, because it will take care, and this at least like system load will run. So fault tolerance in this structure is there. This is the one of the advantage over over this. No, so if you this is a called Vienna. Okay, come to the three level NPC. Say again high power, but like you see, try to see here. Important, interesting here is again there is an option you can go with either one. So three phase people can call it like why do we require this again ultra thin, ultra fast. So those words if you want to use, the high voltage is the best option for us. So in this context, like this structure again will help us to take care. Uh, Okay, this is the another one, three phase, three level ANPC, active neutral point lamp. These are again, you see, these are again gallium nitride devices, and these are again FETs. Again, these are all our WBG devices actually. So why do we, how can we like choose this? Actually, how can I justify this? If you have a, for example, this is a sine wave. What is the three level structure will per unit per leg? If you see, this is the structure. If you see, and then if it is the voltage, if it the case, unity power factor load. If you want to talk about, so you see this one. This is the most important region where if you want to interrupt at this point, voltage also very high, current also very high. So therefore, this is the reason where you are really getting high, more losses than the other one. Yeah, na, this one is like zero crossing. So the zero crossing, whosoever the current and voltage profile also very low in the magnitude. So you can, though if you interrupt that significantly low in the value only loss wise. This is the most important aspect while they are choosing which any topology. So which half bridge they are using to tap the DC positive rails or high voltage, those supposed to be, the standing voltage of those devices must be as low as possible. That's very good option. Another thing is common emitter. If you, I think many of them are must aware about this. If there is a device, suppose like I connected like this, I may not like, for example, like if there is a situation where, for example, inverter, the entire bottom leg, if you see all the devices, multi-phase inverter, if you see, so there's a devices emitter is common to this. What is an advantage? I can use one isolated DC to DC power supply. Uh, One isolated DC to DC power supply to meet this one. Of course, if you see this, what I want to convey here, this one. So these are the DC power supplies. So this DC power supply E needed to pull, push, pull the voltage. If you controller maximum, what you will get, even DSP 3.325 volt. But silicon or some gallium nitride devices needs minus volt to plus volt. Specifically, even our device, like what I've chosen, the device is demanding again. -5 to 15 volt to -5 to 15 volt. That how can you get it? Like you have to pull this. So to pull this, you need a DC isolated DC power supply. How many? Well, look, each and every device needs this. If you have these common emitter configurations devices, then advantages all those devices you can use one power supply because no isolation issue. That is another additional advantage if you try to make common emitter wherever possible, any configuration while you are proposing. So these are ANPC again, active neutral point clamped. Instead of diodes, they use these devices. Number one, though it demands more additional auxiliary power supply, gate driving and all, however, conduction loss is low. Number one. Number two is there is a redundancy if I want to bring the zero voltage level. This is one this thing. And then yeah, one of the article nowadays people are using, instead of direct clamp they are using this T type is bit popular over here. So this is also definitely the processor caller only. So Vienna story, controlled uncontrolled devices are replaced with the controlled devices. But you see, this is one the silicon carbide again. So because it's very clever, it's very simple point. This is 400 and there 400 again. So here it is, the total DC link is like again 800 volt story, plus or minus. So in this context, gallium they cannot use. The obviously they have only one and option, the silicon carbide. Number one. Number two, because this needs to block entire 800. These can be a silicon carbide because it needs to VDC half of the DC link only. So in this context, like silicon is like cheap, well matured in respect of all the stuff, right? You know very well. So the silicon carbide wala, they used it. By the way, I mentioned like minus volts. As you know, this negative voltage will offer this fault turn-on story. If you take it this one, what will happen if I want to turn in, turn off, and turn off, turn on, off, turn off? So this is the voltage here. So what is happening if the moment I turn off, operated with the bit high DC link voltage like 800, this is most one of the dangerous issue. If there is a R again, this is what actually, this is a gate actually, sorry. Sorry. So this is the story. This is R and C, and there is an inductor also. So RLC. So RLC, there is a spike I am giving to the RLC series circuit, is second order system. As you know that this may be possible. So this can be controlled with this R. Not only that, limit this. Now if you see what will happen, If I want to operate with higher this one, so dv by dt is there. There is one more capacitance. You have one more and another capacitance. So and another capacitance. So I want to write better. I'll write here. So better this one. I think there are trans capacitance. These are the this is what actually switch, right? So originally speaking, this is the switch. This is the lead resistance. If you use LT spice, you can develop. You can see the analysis of how it behaves. Really, very bad behavior. If it is like DC, here it is operating. So this value will be significant when the dV by dt is more. Then I is equals to C dV by dt. C already there. The I dV by dt. Then charge current starts flowing, and then there is grounded for the discharge path, and charge there is in one more resistor. Charging must be this and discharging must be another resistance, so that you can operate higher switching frequency. This is a simple point only, but how it really relevant to us? It relevant because of the common emitter configuration. If you do power supply story, you see this capacitor through. If you do this way, what will happen? Yeah. So this there is a voltage will appear. The voltage may be that voltage may be greater than the threshold voltage of VGS of this device. So even I want to turn off, it won't be. So therefore there is a fault turn on. So entire DC link will get shorted, and then damage. So one of in the literature, what my understanding, there are 2-3 approaches. One of the approach is like apply the negative voltage. So the negative voltage gate itself is you apply the negative 2 instead of 0 to 15 minus 5 to something. If you do this, is always what will happen. This negative voltage always there. So then the negative voltage, what will happen? It always tries to at least not cross the threshold voltage of this. So this is the way actually people has mentioned. So therefore, this is one of the approach you can this. So this is another challenge if you want to if you use the other devices like these special devices. Anyway, conclusion is what? If you have like 2 level, 3 level, these are the instead of 3 level, these are the configurations. 400 to 800 if you want to go, right? So how can we do hybridize the existing configurations with replacement of these WBZ devices? Number one, so that like we can address few aspects, specifically high power density altogether. However, few configurations, if you see, few offer few, some of the configurations offer fewer number of devices, and other offers more number of devices. And and specifically the previous one only, this one only. Hardly if you see 1, 2, 3, 6, and single phase, you take it by 3 phase unnecessary. 1 and 2, 3, 4, 4 devices only. If the diode clamp, if you see 4 control devices and 2 diodes. Now diode only the count is sufficient is a question mark. Or do we require to take care another parameter? The parameter is called not only the count we have to take care about the voltage stress also. This is another important thing, standing voltage, because obviously I cannot like design my converter or any power unit randomly, right? End of the day, what availability, which devices are available and what rating matters my design. So in this context, to meet your load requirement, availability at the market we need to check. So therefore conclusion is this: not only device count, we need to take care about the voltage stress. And in addition, like special devices, if it is so, the more it is hybridized, like different devices if you use, right? Obviously handling is not easy, in the sense not much reliable up to my knowledge, because like one is one type of device, another type of device, like something happened or specific device kaha leke aayenge. So that is the also one of the point. So in this context, conclusion is this: we need to take care about not only few performance but like common mode and all. We need to take care about this device count and device stress and some special features also. And again, just I have mentioned in the mining applications, if you see, dumpers are there, heavy vehicles. So there 11 kV motor if you want to run, how it's possible? The battery is there, The battery, instead of if you don't have any battery also, like let it, the rail is there, the rail says either if you want to take it. So the converter has to handle that power rating and voltage rating. So in this context, like if you go further, these are the few like classical structures can use. However, it's a big challenge because this is such a complex, clumsy number of devices. These many devices we need. Not only that, you see, these are also not uniformly working. No, we are not using equally also. The moment if I connected these capacitors and if you charge and discharge equally, no issue. It never be happened with this structure. So because like see, if it is the case, always like there may be this case, there may be there, if I want to tap here, it has to be take care, load has to be take care by this device. So that instant it may charge. So it's always not equal story. So these capacitors voltage will be imbalanced in respect of voltages. If it is in imbalanced, how can I establish this staircase PWM waveform? Whatever the advantage, inherent advantage story can't be. So therefore, for heavy load, agricultural like conveyors or these heavy machinery, if you want to electrify, then what the story? These configurations still they're having their own they're having their own significance. So if it is the case, like number of devices, reliability, efficiency, cost, few parameters, industry always wants it. So in this there are the few patents what they have derived it. See, for seeing it's very clear and simple in structure. However, I just have mentioned it. So device stress is most important because availability matters, number one, right? Another one is efficiency, right? See, if you see, these are all in this context, yet structure, no, V naught only, but this is also V naught, V naught, and but these needs 2 V naught, 2 V naught, and 2 V naught. For these are also 2 V naught, 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 and 2 V naught, and V naught and V naught because it's tapping at this point. This one, you see, this is a very interesting story. This is called nested, they mention, like a nest. See, it seems very simple structure, right? Very simple. Operational wise, fault identification wise, very simple. However, you see this, these needs to block this much, and these needs to block like 3V, 3V, 2V. So one of the device needs to block 3 are V, or V are 3 are V are 3. So if I'm not wrong, I think so. These are the correct only. But anyway, these are not our most main interest. These are the interest. Device count is very less in number. However, the stress you talk about, very. For example, even if you want to operate 800 volt pack, total 800, 200, 200, 200, 200, it needs to block 1200, right? Not only that, another thing, okay, here you see this. Previous one is more in number, but stress wise very low. That is the one advantage with the classical configurations, but these are having their own advantage and disadvantages. So I want to, yeah, you see this. For example, this is a voltage waveform and this is a current waveform if you, right? So just I have mentioned it, this is my reference, zero reference. So this one is like causes unity power factor, of course, UPF. So here it is the more current time chopping, large value, peak value, and voltage also at peak value. Both are peak, and then it will definitely causes more and more and more losses. So for example, the positive voltage, if I want, I need to turn on this, and then I need to turn off, turn on, turn off, turn on, turn off. The moment if you want off and on and off this one, because I need a PWM story, no? I don't want a control one, continuous one, rather it is the story. On and off and on and off and on and off. It is off. Voltage will be how much? 4V. If it is on, okay. Off, on, off, on, off, on. In the sense, there is a high voltage appear across, number one, and number two, it also needs to the highest large value. So the whichever like the peak slab we are synthesizing, and that half bridge supposed to needs to less voltage blocking. That's very good. Like this one, this is very good in this respect actually. But however, it is very poor and it causes the highest losses in the all the configurations, and efficiency wise very poor in performance. Of course, definitely these are, you see this. Dekho, this is the common emitter and common emitter. These two needs only one, and one, two, three needs only one auxiliary power supply. One, two, three, four needs only one auxiliary power supply, and that's what. Four needs only one. Four needs one. It's very good in respect. Second is fault tolerance. Something happened, no problem. What will happen? Hardly. Shape is not a five-level staircase. Rather, it is like there won't be a V. There may be a
भरपूर आहे नाही.
कुठे आहे आता? घरी बसले.
आज उद्यासाठी परवा आहे वाटतं.
आता हे चांगलं आहे भावाचं.
someone is like unmuted. Can you please mute from your end? Yeah. Yeah. So therefore, the point is, yes. So what will happen if it is some failure happened, like, here? Doesn't matter. It won't be there is a 2V and V won't be there, but however, it's not symmetry. But still, for motor load, it will okay, chalega. So similarly for this story also, this is the story also. This is one of the advantage in this configuration. So that is the point. So I think you are understanding this context. Like, this is another modified T structure only. So this one, if you see, this is one leg, and this is another half bridge, and this is another half bridge, and this is another half bridge. So using the four half bridges in this structure such a way that will synthesize the 5-level staircase PWM waveform here. And also the advantage is this. See, you see this here, it needs the V and V and V, and also V and V and V. This needs a 3V, of course, and then 2V and 2V. Comparing with the previous one, the stress across the devices low, and the devices which needs the more blocking voltage also low. So this is most important, one of the important observation. Another thing you see, but it seems like asymmetrical. So if you want to synthesize this, or otherwise want to bring this one, this voltage to control the current, 1, 2, 3 devices are in the continuous conduction. The secondary, the negative side, if you see the 2. However, you see this is the 3V and V, and this is again 2V, VV, more or less 4 volt only. So though device count is less, but because of this, unequal standing voltages, so the loss is more or less, it's not unsymmetry, and more or less same, and then we don't have. Actually, can you please mute someone unmuted? I think they are traveling. I think Kerala only. Some of a friend from Kerala. I think so. You are traveling. I think so. There is a raining. Please, can you unmute from your end? Yeah. Yeah. Thank you. Yeah. This one is this is the important what observation. It's not as like appear. It's not asymmetrical. Rather, it is also behaves like a symmetry only due to this unequal voltage values of a devices. And this is one of the important point while you are choosing. These are the few comparative points. If you see this, bringing something into the existing this one platform, instead of using a simple devices, any converter, if you want to design for high power specifically, the devices, the few parameters must be taken care. So here what actually the most switches and number of control devices along with the number of stress also, and then these like whichever offers the lower value overall together, it's absolutely good. And another thing, you see this, the interesting observation is this: it is the 1.7 kV and 3.3 kV. Current rating is same. Cost is not exactly double. There is a significant change. Number one, whosoever having whichsoever topology needs different voltage ratings, and the two highest voltage standing, high standing voltages, their per unit value is very high. So per unit value is very high because needs more, no, they go 4 times the battery and to this. So the more it is, the obviously cost will be high. The industry doesn't want it. Efficiency story देखो, this is 1.7 wala and 3.3 wala. If it is 3.3 and the on-state resistance is more or less this, and then these are the like device, this one ABB, the on-state resistance is more or less double. So conduction losses will be more or less double, right? So this is another disadvantage. So what I want to convey here, the device count alone is not sufficient. Rather, needs to take care about stress voltage, standing voltage across of different devices, and the number, if it is low, it's very good actually. That's the point. And yep, I just have mentioned this. There's one of the constraint about this structure is imbalance of voltages across these capacitors. So voltage, hysteresis controller is one of the classical and best controller to control the current if you want. But however, I told you it's a load sensitive controller. So hysteresis controller
You are not audible now, Dr. Naveen. I think your mic has been muted.
oh, how? Someone is accessing. Check.
Now you are audible, Dr.
Sir. Acha, I don't know. I don't use anything. Okay, okay. So if you see this, then how can we control it? Obviously through controller if you want, right? Uh, these are the node points. If you avoid if you avoid, you cannot get the, if you see, logic kya hai? What is the simplest point? I want to control my current such a way that I want to bring some voltage levels here. That's number one. And then inherently this structure is offering this wave shaping, because 5 level will offer per pole. Otherwise, line to line it will be a 9 voltage, 9 level. It's obviously it's offering. I don't want to. No, I don't choose these configurations to wave shape. I choose this to meet the high voltage, uh, electric, high voltage, machines if you want, right? So in this context, if you avoid this, if this one 2 and V and 0 minus V, this is minus 2. This is the simplest way. So these are the level structure like 2, 1, 0, -1 and -2. If you don't want tap for longer duration, what will happen? There is a suppose like common, the commonality between high and this case. Then what will happen? This I can make the this I can charge balance can be possible through controller itself. For example, you see this one. If I don't want to use, no problem, don't use it. That instant, what will happen? The capacitors are not balanced, and the deviation, if you see, if you take some deviation, if you keep, for example, this is the deviation if I kept between this one, it is not purely 5 level. So if you see this one, exactly all the DC link capacitors are balanced nicely by using a balancer. Then the 5 level staircase also possible. If I want to using only this story, so therefore like I have to sacrifice with this voltage balancing story, and then 2 level, it acts like a 2 level. So, but like THD obviously will increase if it's that's what it's a very clear point. The more smooth pole voltage it is, the current will be inherently will address. So this is the another issue, the constant issue with the multi-point clamped structure configurations. But however, back-to-back converters like AC to DC and DC to DC, or AC to DC or DC to AC, there is a common DC link wherever you required. These are the these are the options actually. And this is a doubler again, and this also doubler will offer like double the peak voltage here. And I mentioned, right, you can use this for directly here. You will get these structures. No, this wala structures milega. This you will use for high frequency transformer, and you process and again rectify it and filter it. So single staging charger people used to call it as. Even two stage also if you want you can, no problem. But single stage is very good option because that inverter side or DC side front end DC AC wala AC that you no need to use it. So there we can use with the same structure. Restricting unity power factor strictly and control devices can be replaced with uncontrolled, but obviously where we require it is. So only AC to DC applications you can. So this is the case where, uh, yeah, the challenges you see. Most important, I mentioned it like what we learned here, the power design. So power supply design for gate. The classical devices, classical driver circuit, TLP, no, I don't think so. Please don't use those. No, even 3 series also. Now the different devices are coming. Just I have shown you. In fact, that is like SMD. It can operate with 800 kilohertz very nicely. Powering instead of using that bulky, transformer, linear regulator. Better use. There are different ICs. Okay, I'm not advising you to purchase directly, but if you want to make your system bit rigid and more rely like fault, what I can say, like it's more rigid, better you go with one time design so that can used for all the different devices. So you try to adopt a universal driver, so with the small modification can drive 0 to positive, minus to positive, or whatever you want. So power circuit design is most important. Otherwise, what will happen if they suppose 4 devices? The previous structure, if you see, the 4 devices needs the one sufficient power supply. It seems very good, but like for that power supply again, you need to AC to DC rectify it with through transformer only. If you are not choosing proper transformer, they get pulse cannot be driven. That is the most one of the important observation. The second is filter. I just see controller, which control we have to. For example, hysteresis, if it's load sensitive, how can we design the static filters? It can't be. If that is always changing to dynamic filter kaise change kare? It's not easy to design. So if for example like LLC frequency, resonant converters DC if you see, those are frequency modulated, frequency operated. It's not pulse width modulation. So second, like designing this filter such a way that choose the appropriate core turns, otherwise these get saturated. And wiring, yeah, this is another important. Instead of use single strand, use the multi-strand like leads. It's the advisable option, and we have verified with the single strand what leads wire. So leads, someone is unmuted. Can you please mute? Leads wire really, leads wire is giving very good, good progress actually, very good satisfactory results. With low resistance, this, can you please? So therefore, lead is the important option, and a snubber circuit design across switches. So the snubber. A snubber also will help us to like ZBS. sometimes. There are other approaches or other advantages also. So like turn off number, turn on में we are not actually off में ही generally हम लोग ज़्यादा कोशिश करता है. So these are the few aspects. These are the few reasons and for your to like what how verification of the concept. So the bidirectional. So this is the bidirectional story. And, yeah. Interesting. This is
Some noise is coming in between. Dr. Naveen Yalla.
sir. Yes.
Now your voice is not clear as it was earlier till now.
Is this my issue?
That's up. I think voice is clear. I am also listening. Might be some issue at your side. Dr. Naveen, your voice is pretty clear.
Anji, yes. There is a echo. There is a disturbance from someone else also. That's what. Yeah, if you see this, yes, someone is unmuted. Maybe that disturbance is. Anyway, so you see this. So this is called the last nested one. The last one, what we discussed on nested, is very interesting. Obviously, you see this one, a very poor performance. This is what actually I want to like conclude. The topology.
Naveen Saab.
Sir, tell me.
Now it is disturbing.
From my end, sir.
No. I think some participants.
Yes, someone else has open mic. It is advised.
Some participants. Yes,
Neha has just mute yourself. Neha has. ठीक, fine. Now, Doctor, please carry on.
Sir, yes. Now, sir, I think it's very clear from my end also. So this is what actually interesting observation. If you see the nested, which is having only 1, 2, 3, 5 devices, people are claiming. You take it like bidirectional device as a single device. But what is the performance parameter efficiency? If you see 94, it is very poor. Not poor, significantly low. So device count alone is the only important parameter. Rather, the voltage stress, standing voltage, also most important, because already 98% is people achieved, and introducing something to meet your requirement, which is really disturbing or bringing the efficiency back to the poor value. What is the logic? So these are the few aspects, and then front end, its main aim is to take care about the power quality also. So these are the few aspects, and then conclusion is this: you can work on like any configuration. Like the power density is absolutely one of the important for OBC. That is what I want to address. How can we minimize the filter or passive element size? One way you can use like active power decouple, active APM integration while integrating auxiliary power module. Use those filter to filter the harmonics and like process like AC to AC. See that there is no any two-stage story. And for medium voltage, high power, if you talk about the conventional two-level story won't be well possible if you want to go with silicon devices. If you want to use this, WBG devices, which are having inherently good characteristics, electrical characteristics like junction capacitance values are very low, and on-state resistance is almost very low. These are offering really positive points for us in respect of like if you want to efficiency, all the stuff, right? So obviously we have to adopt. The new devices are coming. It's not the case like okay, naya aa gaya, so why? So new came into the market, so blindly we cannot go, obviously. And then if they are really giving a positive aspects, and that too, it's not all over. It's a specific domain specific. So space is most constrained. Like you can go with the WBC devices. So just even I have given the 2 case studies, like specifically for Coal India, Northern Coal Limited. Second is Reliance Power here near UP. So they are already working on it, and they are like very aggressively they are moving towards the mining industry to the electrified instead of diesel. So ye hai story, and this way, thank you for this opportunity. If you want, please you can also.
Thank you, Daksab.
Sir.
It's really wonderful. Actually, I can see some question from the audience. Just let me ask. One question is from Pradeep Kumar. How to design C_DC?
मतलब capacitor for DC, I think so. I
Yes,
don't.
I hope so. He is asking about capacitor for this removing. If Pradeep ji is available, just tell us the question so that Dr. Naveel can answer.
I think so. If
And
you, yeah,
yes, I think he is asking about the capacitor.
yeah,
How
yeah.
to
So
design the value of the capacitor so that the
see,
ripple can be
actually,
minimized.
yeah, very. I think Pradeep, this is very. One thing is, why do we require a capacitor? One is like the moment you want to if you are converting AC to DC, while converting DC again depends on like single phase or three phase. If it is single phase, the dominant will be what? A 2 omega along with switching frequency. Those frequency needs to be filtered. That is the one important. Then only we can at least expect like stiff DC. In the layman language also you can say. So the 2 omega, or if it is three phase, there is no 2 omega story. So which is the harmonic current if you find it, right? So current can be average model if you take it, that you can find the RMS average current through the DC, right? With individual harmonics. So that current which is passes through your capacitor, which is having like ESR. So that has to be taken care. So if you see the curve actually, capacitor versus this, use current occur at the inductor Y, IL. So that is the one important aspect. One is a life and another one is ripple suppression. So these two you need to take care. If it is like for example 10 voltage ripple I am allowing at the DC side, so accordingly the CdV by dt and then which frequency component you involve it, you can get it. I can refer this, I can refer you application note of, even uh, Toshiba you take, Texas Instruments you take, you can find this relation very clear way. But I've given, I think I mentioned you. And someone asked you what DC-DC? Inductor current is very high. Inductor current is very high, so it's no. It's why it is so. For example, what type of converter you are talking about? If it is isolated converter, let it like resonant.
I
LLC.
hope Dr. Saab, he may be talking about the boost converter because only in that particular case our inductor gets short circuited and huge amount of current is flowing.
See that non-isolate. Okay. Yeah, yes, sir. Yeah,
Yes.
exactly, sir. Yes. What you are. See, Ulta, you please take it another way. Design always, once you fix the boundaries, right? So current will increase or decrease while you are chopping, definitely possible. Hai? The load is demanding, they're supposed to current come from the source. That is secondary. No, but the question is like this. If you fix 1 watt, 10 watt power, voltage you fix, then you try to find out how much current it is. The current, which current you have to take care about the RMS current, right? On and off, you are chopping the current and you are operating with some specific frequency. So what is an RMS current through the source or through the inductor? Number one. Once you have that inductor value, RMS value, that much of current density wire you have to choose. And then after that, how much inductance? Again, do I require to continuous conduction or otherwise discontinue? It's up to us. So I don't want to use a large inductance value, use the discontinue so that like will be ripple will be high, no problem. So it's all about like what you want. It's continuous, some X value will come inductance. Then L you have to choose such a way that you this area product story, then choose the material and make the inductor and then control your converter so that high current ka story aayega nahi actually, that we it's our duty to control it. Why it is coming, Obviously, you are chopping and you are like, drawing the current. That is the one. Uh, current is increase. Why current will increase? Current's not supposed to increase if you choose properly. That's it. There is one thing, is the PFC, boost PFC if you have. So like conventional classical bridge rectifier and that stuff, if I'm not wrong. There, if the electrolytic capacity is not precharged, what will happen? It draws huge current from the source. That may causes the saturation storm. You need a precharge to avoid to inrush instant current from the source. So I think I answered your question.
Yes, yes. Thank you, Dr. Saab. Participant said, okay, you are so fortunate that the participant is satisfied. I hope he or she got the answer. And really, I am very thankful to Dr. Naveen for sharing such a wonderful talk, starting from 3-level inverter to come up with 9-level inverter and various type of isolated and non-isolated converter and with the various P devices. It's really wonderful talk for all of us, and I hope it will open various dimension of the research. You just ignite what could be the possible solution for getting the higher number of level of inverter with using reduced number of count. I hope the faculty members, the researchers who are involved in this talk, who participated in this talk, as the lecture is already available on the YouTube, I will share the link to you. They will get benefited and they will do something related to this topic in their research. So once again, very much thank you, Dr. Naveen, for your
Sir, thank you.
wonderful.
Like I really thank you, and many after many days I saw you. That's important, and this is a nice opportunity to meet you. In fact, so we are family, like very well.
Yes, yes, Naveen. Of
And
course,
during the journey also, like see, it's our end of the day, sir. Senior is senior. You trained us
and that
during.
is the rule of BTech that the once the senior always
Yeah,
senior.
yeah, yeah. You.
And see, we all are faculty, and I believe being a teacher, we must always remain as a student. We must learn from each other. We spread the knowledge what little bit we have, and that is why we are associated. Even I have completed my PhD in 2016, and now it is 2026.
10
So
years.
the relation, that is the brotherhood which we have developed during stay at IIT Roorkee. Actually, I tried for Sanjeev as well. Yesterday, Sukanta took one lecture,
Yeah,
and in
yes, yeah.
evening, Kishore was there. Now you, and tomorrow we have Rakesh Maurya Saab.
Acha,
So
our senior. Entire our
I
team.
always try to get as much as I can our Professor Pramod Agrawal sir is student, and I also take one talk on Friday. So it's all the Siksha what we get from Professor Pramod Agrawal sir that we are trying to spread all over the world.
Yeah, yes.
Thank you once
Yes,
again.
sir. Thank you. Sir, Gulswami sir is there.
Hey, Sanjay Kumar sir, how are you?
Sir, I am good.
I am good. I am good. ये तो छोटा रुड़की बन गया. Small रुड़की.
Hey, Naveen, how are
Great,
you?
sir.
I am good, sir. I am good. Sir, how are you?
See, I've been waiting for you that, I may get a chance to talk to you.
I am always available, Guru Swami Sahab. I am always available. And very nice. We also have Afroz Alam with us. Afroz ji, if you are ये देखिए Afroz ji is with us.
Namaste.
sir.
He joined here on the HBTU, and Sailen ji is also there. Sailen ji, अगर आप हो तो देखिए एक बार IIT रुड़की का मिलन हो जाए.
Definitely, sir. I think probably it is a very good opportunity to meet all of our alumni from IIT Roorkee. This is the one of the platform you have created.
Special thanks to Sanjay sir.
And Guru Swami sir, this lecture is live, so this moment will remain in the air forever and ever. That is the best
definitely,
part.
sir. I think probably we'll have more discussion in the coming session also.
Yes. It totally based on the electric vehicle. It's
Yeah.
real-time simulation and MATLAB simulation. And
I am
also
teaching the electric vehicles for our 6th semester students in our college as an open elective course.
very good, Guruswamy sir. So next time your number will be there.
Yeah, definitely. Likewise, I'm ready.
Okay. Definitely.
Yeah.
Next lecture would be yours. In fact, I used to conduct this expert talk under the umbrella of IEEE Power Electronics Society. So
I am
we
the
will have
parents advisor in my college.
Oh, great. Great, Guruswamy sir. I'll call you after the meeting. Huh?
Yeah,
Yes,
definitely, sir.
Yeah, thank you,
So,
sir.
Yeah,
thank
nice,
you.
nice
Thank
meeting
you,
you.
Nadeem Saab,
Okay.
once
Okay,
again.
sir.
Bye. And
Bye.
dear participant, don't leave the session. At 5:40, we will start once again.
Okay. Thank you, one and all.
Thank you, sir.
Thank you.
Thank you, sir. Thank you.